All right, welcome back. So we've talked about finding the slope at one specific point on a curve, but what if we want more? Today we're going to build this incredible new tool, a function that can tell us the slope at every single point on a curve. It's a total game changer. Let's get into it.
So here's the plan. First, we'll tackle the big problem, why finding slopes one by one is just not going to work. Then I'll introduce the elegant solution, the derivative function itself. After that, and this is the really cool part, we'll see how the graphs of a function and its derivative are basically talking to each other. We'll also cover the exceptions, when this whole thing breaks down. And to wrap it up, we'll even peek at what happens when you take the derivative of a derivative.
Okay, so we've got the machinery, right? We can pinpoint any single spot on a curve and figure out the slope of the tangent line right there. But what if that's not enough? What if we want the big picture? I mean, how do we understand the steepness of the entire curve, everywhere, all at the same time?
Think about it. For a straight line, it's a piece of cake. The slope is the slope. It never changes. But a curve? Whoa! The steepness is constantly in flux. It's going up, it's flattening out, it's diving down. How in the world can you capture all of that dynamic information in a useful way?
I mean, sure, we could just sit here and calculate the slope at point A, and then do it all over again for point B, and then for point C, and on and on. It works, technically. But you can see the problem, right? It's just so inefficient. If we want to get a feel for the function's overall personality, this one-by-one approach is a total dead end.
And yeah, inefficient is putting it mildly. The source material nails it when it says this process would get, and I quote, quite tedious. They're not kidding. There has to be a better way. We need something more powerful, something that does all the work for us. What we really need is a function.
And that, right there, brings us to the star of the show, the derivative function. This is the elegant, powerful solution to that super tedious problem we just talked about.
Okay, so here's the big idea, the core concept. The derivative function, and we call it f prime of x, it's basically a slope-finding machine. That's the best way to think about it. You take your original function, f of x, and you feed it into this machine. And what does it spit out? A brand new function, f prime of x, that is literally a formula for the slope of the original function at any point x you can imagine.
Let's make this real. Say we've got the function f of x equals x squared minus 2x, okay? We take that, we plug it into our derivative machine, the gears turn, the limit definition does its thing behind the scenes, and out pops this beautiful, simple new function, f prime of x equals 2x minus 2. And just like that, we have a complete map of every single slope on that original parabola. Pretty amazing, right? But here's where it all comes together. The real magic, the aha moment, is when you visually connect the graph of the original function to the graph of its derivative. This is where it all clicks into place. Think of this table here as your secret decoder ring. It's super simple. When the original function f of x is going uphill, increasing, its derivative, f prime, is going to be positive. That means its graph will be hanging out above the x-axis. When the original function is going downhill or decreasing, the derivative is negative. It's below the x-axis. And the key moment, at the very top of a hill or the bottom of a valley, where the slope is perfectly flat, the derivative is 0. It's going to cross the x-axis right at that point. Okay, let's put our decoder ring to the test with our example. Look at the left side of that parabola. For all the x values less than 1, see how the curve is heading downwards? That means its slope is negative. Now look at the graph of its derivative for those same x values. What do you see? That straight line is living in negative territory, completely below the x-axis. It works perfectly! All right, now zoom in on the most important point, the very bottom of that parabola, the vertex, which is right at x equals 1. The tangent line there is perfectly horizontal. The slope is 0. So, what does our theory predict? The derivative should be 0. And look, right at x equals 1, the derivative graph slices right through the x-axis. It's a perfect match. And to complete the picture, check out the right side of the parabola, where x is greater than 1. The curve is climbing, right? It's increasing, so its slope is positive. And its derivative? Sure enough, that line is jumped up above the x-axis into positive land. See? This visual connection is so powerful. The derivative is literally telling the story of the original function's journey.
So, this all seems great, but does it work for every function? Can we always find a derivative? Well, not quite. There's a catch. For a function to have a derivative at every single point, it needs to be, let's say, well-behaved. The more technical term is smooth.
And this brings up a really key relationship in calculus. Think of it this way. Being differentiable, that is, having a derivative, is a much stricter club to get into than just being continuous. If a function is differentiable at a point, then it absolutely must be continuous there. No ifs, ands, or buts. No breaks, no jumps. But, and this is the important part, it doesn't work the other way around. A function can be perfectly continuous with no gaps at all and still not have a derivative at certain spots.
So where does it break down? What are the troublemakers? Well, there are three main culprits to look out for. The first one's obvious. Any kind of discontinuity, like a break or a jump in the graph, that's an automatic no-go. But the other two are sneakier because they can happen on graphs that are totally continuous. We're talking about sharp corners, or points where the tangent line goes straight up and down. Let's look at the classic example of a sharp corner, the absolute value function. You know, the one that looks like a V. It's totally continuous at x equals 0, right? You can draw it without lifting your pen. But think about the slope. On the left side, the slope is a steady -1. On the right, it's a steady +1. So what is the slope exactly at that sharp point at the bottom? The function can't decide. It changes instantly. Since there's no single, well-defined slope there, the derivative just doesn't exist at that one spot.
Now, here's a trickier case. Check out the cube root of x. It's a beautiful, smooth, continuous curve, no corners in sight. But look what happens right at x equals 0. The curve gets so steep that its tangent line goes completely vertical. And what's the slope of a vertical line? Well, it's infinite, or, undefined. And since the derivative is the slope, we have a problem. The derivative is undefined right there at x equals 0. Okay, so let's pause for a second. We established that the derivative, f prime of x, is a function all by itself. So that leads to a really interesting question, doesn't it? If it's a function, can we take its derivative? Can we find the derivative of the derivative? And the answer is a resounding yes. And when we do, it unlocks a whole new layer of understanding. We call these higher-order derivatives. The next one in line is, you guessed it, the second derivative, and we write it as f double prime of x. All it is really is a function that tells us the rate of change of the first derivative. It's the slope of the slope function.
Now, the best way, the most intuitive way to wrap your head around this is with a real-world example from physics, motion. Imagine you have a function, let's call it s of t, that tells you an object's position at any time t. If you take its first derivative, you get its velocity. That's the rate of change of position. Now, what happens if you take the derivative of velocity? You get acceleration, the rate of change of velocity. See the pattern?
So you can see how each derivative peels back another layer of the story. The original position function just asks, where is the object? The first derivative, velocity, asks a more sophisticated question. How fast is it moving, and in what direction? And then the second derivative, acceleration, asks, and how is that velocity changing? Is it speeding up? Slowing down?
Okay, let's boil this all down. What are the big takeaways here? Number one, the derivative f prime of x is way more than a single calculation. It's a whole new function that gives you a complete roadmap of the slopes of the original function. Number two, the graph of the derivative is like a secret storyteller for the original function's behavior. It tells you everything. Number three, not all functions get to have a derivative everywhere. They need to be smooth and continuous. And finally, number four, we can keep going. We can take derivatives of derivatives to describe things like acceleration, which is just the rate of change of another rate of change.
And that leaves us with one final, fascinating thought to chew on. We know the second derivative is acceleration, which is the rate of change of velocity. But what about the third derivative? What would the rate of change of acceleration even mean? Well, think about when you're in a car and the driver suddenly stomps on the gas or the brake. That sudden lurch, that's a change in acceleration. Physicists actually have a name for this third derivative. They call it jerk. And it just goes to show you how deep this rabbit hole goes, all starting from the simple idea of finding the slope of a curve.